You can start, Rohan.
Okay, so for now, I'm going to skip the first problem and come back to it later. So I'm going to start with this problem, which is the first combinatorics problem from the IMO shortlist. And
Rohan, people may not know what ISL is. Can you describe what ISL is quickly?
the IMO shortlist is a list of problems out of which IMO problems are selected for either that year or the next year. And usually C number ones correspond to IMO number one difficulty. And this problem has a relatively simple problem statement. It's asking for the amount of permutations of the first n integers, satisfying this inequality. But it seems the condition seems a bit weird and hard to deal with. So I think the best way to approach this problem is to just try listing out the first few, like solving this manually for small n. For n equals 1, the only permutation is 1. For n equals 2, both the permutations 1, 2, and 2, 1 work. For n equals 3, 1, 2, 3, 2, 1, 3, and 1, 3, 2 all work, but we can see that no other permutations work. And for n equals 4, 1, 2, 3, 4, 2, 1, 3, 4, 1, 3, 2, 4, 1, 2, 4, 3, and 2, 1, 4, 3 all work. And if we continue going to larger n, it becomes a bit tedious to write things out. So for now, we can try to look at these permutations and see if we can observe a pattern. And indeed, for n equals 4, 4 either shows up in the rightmost spot or the third spot. And if it shows up in the third spot, it must be followed by a 3. And then it's just the amount of permutations for n minus 2 in this case, and the amount of permutations for n minus 3 in this case. But we have to prove that 4 cannot be earlier than the second to last spot. And we can do that by, again, seeing how this works out for n equals 4. So let's say we have a 4 in the second spot. Then we have the first two integers. There is only one spot before the 4, so one of the integers must go somewhere here. And that integer must be 2 and it must go here, or else the inequality won't be satisfied. And then the 1 cannot go here, so it must go here, and the 3 must go here. But then this is bad and it does not work. Wait, no, I mean this is bad, does not work. And in fact, this is the largest number n, and let's say it goes in the mth position. Then out of the first m numbers, at least one must be to the right of n. And in that case, we have that m times I, which is where m is greater than or equal to n times m. But I has to be an integer between 1 and n by definition, so that implies that I is equal to n. And since equality holds here, if we go back to the problem statement, equality must hold for everything between it. And we can see that if n minus 1 is to the left of n, then there also must be another number smaller than n to the right of n, and then it will no longer work. So n minus 1 must be somewhere to the right of n. Let's say n minus 1 is at position A. Then we must have n minus 1 times A equals n times m. But GCD of n and n minus 1 is just 1, which means that as A and m are both between 1 and n, we must have that a is equal to n and m is equal to n minus 1. Therefore, if n is not in the nth place, it must be in the n minus 1th place. And then this recursive condition holds. So if we call the answer f of n, then f of n equals f of n minus 1 plus f of n minus 2. And then this is just the shifted Fibonacci sequence by the definition of Fibonacci sequence. And the reason this is one of my favorite problems is that this doesn't use any high power techniques. It's just working with examples and observing patterns. Are there any questions?
Can you summarize it once, Rohan?
Oh yeah. So by looking through a few examples, we can notice that the largest number usually is not near the front. It's either in the last place or the second to last place. And if it's anywhere to the left of that, we can use proof by contradiction and to show that there must be a smaller number to the right of n, and that smaller number must be in the nth place. And from there, we get that the inequality condition of the problem statement turns into an equality condition. And by considering the fact that n and n minus 1 are relatively prime, we can find a contradiction. Are there any questions? Okay, moving on to the next problem. So this is a more complicated problem statement. This is also from the IMO shortlist. It's the second number theory problem. And its problem statement is basically saying for a prime p, you draw an edge between two numbers m and n such if and only if p divides n squared minus m plus 1 times m squared minus n plus 1. Or in other words, this is congruent to 0 mod p. And we want to show that there exists some group of k islands such that you can reach for any two islands in the group, you can reach them through a series of ridges and edges, but you cannot reach any island outside of that group. And the condition about not being able to cross, it seems a bit confusing, but it's just saying that you can only go between two islands if there's a bridge between them. You cannot, like if there's 1 to 2 and 3 to 4, you cannot go along the bridge from 1 to 2 and then just change and go to 3 or 4. And again, I think a good way to approach this problem is to consider small primes p.
Rohan, can you 1 minute explain what is it asking to prove?
Didn't I already explain that? You want to find a group of islands such that for any two islands in the group, you can go between them, but you can't get to any island outside of that group. Anyway, I think a good way to approach this problem is to again try small numbers for p. For p equals 2, actually that's too small, so I'm going to start with p equals 5. We can consider what's connected to 1 because that's easy to work with. Either we have n squared minus 1 plus 1 is 0 mods p, or n minus 1 squared minus 1 is congruent to 0 mods p. So here we have n is congruent to 0, and here we have n is congruent to 1 squared plus 1. And we can continue this for a bit, and we get 1 squared plus 1 squared plus 1. This squared plus 1 and all of those are also connected to 1. Even already for 5, the squared condition is a bit hard to deal with, and it's even harder to generalize it for all primes p. So we should try to eliminate this. And we can do that by assuming there exists x such that x is congruent to x squared plus 1. This means that x squared minus x plus 1 is congruent to 0. So x is congruent to 1 plus or minus the square root of negative 3 over 2 by the quadratic formula. And for now, we just assume this exists. And we will deal with this later. We can call A the plus and B the minus of this. Then we can consider x as one of those for now. We have that n is connected to x if and only if either n squared minus x minus 1 is congruent to 0 mod p, or n minus x squared plus 1 is congruent to 0. But we have that x is congruent to x squared plus 1. So this is just n squared minus x squared is congruent to 0. And this is n minus x is congruent to 0, which means we want p divides n squared minus x squared times n minus x, which is n minus x squared times n plus x. So either n equals x or n equals minus x. This case we don't need to worry about because it can't reach any other bridge if it can only reach itself. So we have to deal with the n equals negative x case. For convenience, we define y equals negative x. Then we can repeat this. We have actually one thing I should have tried first. We have this condition, and we want to see if we can. This means that n squared is congruent to x minus 1. And we want to see if we can guarantee that this is never true, that x minus 1 is never a square. And if we can prove that a minus 1 times b minus 1, if we can make this not a square, then one of those must also not be a square. They can't both be squares. In which case we just choose that one and it's only connected to itself, and then we're done. However, we would find that a minus 1 times b minus 1 is 1, which is always a square. So this attempt does not work. Now we have to try again with y. We have either n squared minus y minus 1 is congruent to 0, or n minus y squared plus 1 is congruent to 0. And we also have that y squared plus 1 is congruent to negative y by definition, as this is just what happens when you substitute it into x is congruent to x squared plus 1. So from this case, we get n plus y is congruent to 0, which means n is x. And from this case, we have n squared is congruent to y minus 1. And this we do not have a simpler form for. So instead, we can try to use the same approach we used here. Okay, so we have negative a minus 1 times negative b minus 1 is a product of the two values of y minus 1. And this becomes 3 plus root negative 3 over 2. Actually, I think it's negative 3, but it doesn't really matter. Times negative 3 minus root negative 3 over 2. And if we expand this, we get 3. And this is good because we haven't yet chosen p, so we can choose p such that 3 is not a square. And we also need negative 3 to be a square because we assumed that a long time ago. And so far, I think this part was most of the problem. This wasn't on the IMO, so I'm not sure how it would be graded, but if I were in charge of grading it, I would give progress up to here at least a 5. And this has all been mostly low power technique so far. And from here, the only approach I know of is a bit more high powered. So between these two things, we see that -1 is not a square. And from quadratic residues, this implies that P is 3 mod 4. And then by quadratic reciprocity, this must be equal to -1 because P is 3 mod 4.
And can you write those terms so that somebody looking up later can look them up?
I don't know the exact term for this thing, but it's like -x. Actually, I think Fermat's Christmas theorem implies this. So this denotes 1 if 3 is a square mod P and -1 otherwise. And the actual formula says 3 minus 1 over 2 P minus 1 over 2, and it generalizes for all odd primes Q instead of just 3, but this just evaluates to an odd number because P is 3 mod 4. And since we want 3 minus 3, I'm not sure how to say this, but we want 3 to not be a quadratic residue. So we want this to be 1, which means that P is 0 or 1 mod 3. And we could just go with P equals 3, but we can also just ignore this condition. And these two combine to P is 7 mod 12. And everything we have done up to this point shows that all 7 mod 12 primes work. So by Dirichlet's conjecture, no, theorem, there are infinitely many primes. And one thing I noticed that this doesn't show that the only primes are 3 and the 7 mod 12 primes, because we don't need x and y as we define them to be the ones not connected. We just chose them because it was simpler to deal with. And in summary, what we did is.
So Rohan, when you're doing a summary, each step explain the motivation, what you were trying to do.
Yeah. So by trying out a few examples and experimenting with them, we can find that the x squared plus 1 condition that's derived from this is very annoying to deal with. And instead we can try to sort of eliminate it by setting x equals x equals x squared plus 1. And by doing that, we can find that the only bridge connected directly to x is -x. And by trying a similar approach, we see that the only bridge connected directly to -x is x or the square root of -x minus 1 if it exists. And by using the fact that there are 2 possibilities of x, we show that one of them works and one of them doesn't work. As in, one of them satisfies -x minus 1 is a square and one of them doesn't. And then from there, we were able to find the values, the restrictions on P such that our assumptions were true, and then the problem was finished. And again, the reason this is one of my favorite problems is because the motivation for the x is congruent to x squared plus 1 was interesting. And I also like these ideas of trying small cases until you notice something, whether it's a pattern or it's just, this is annoying. And also, again, this problem was mostly low powered until the end. And in my opinion, the end shouldn't be worth that much. So I consider this problem as mostly low powered. Anyway, are there any questions? Okay, I'm moving on to the next problem. So here This is from the USEMO number 1, or it was also JMO number 2. And this problem, you have a grid of A plus B plus 1 cells, of which some number are at least amber and some number are at least bronze. We can call this B and this A for convenience. And we want to choose A of the amber cells and B of the bronze cells for such that no two are in the same row or column. And this is slightly similar to like, I mean, the problem statement is slightly similar to where you're trying to choose a few squares that are not on the wrong law, that are not on the same row or column. And there are unfactorial ways to do that, but that's the problems themselves are different. And because here there are two different colors, and also you're not getting this A plus B plus 1 cells, you're only getting A plus B cells, although the size of the grid is A plus B plus 1. And this is a very complex problem that is hard to approach. And when these problems are hard to approach, one method that should be tried is induction. So first we can consider what the base case might be. It seems intuitive that the base case would be A equals 0 or B equals 0. So these are symmetric, so we'll just consider this. And we want to show that it holds for any A and B equals 0. These two are separate. Also, the problem said A and B are positive integers. We're going to prove this for non-negative integers, because if we can show it for non-negative integers, then we've also shown it for positive integers. And I found that proving the base case for induction for B equals 0 was already non-trivial, and I didn't want to make it even more complicated by doing it for 1. So for B equals 0, we can have A plus 1 by A plus 1 grids. So this is for A equals 4. We have at least 16 amber cells and at least -4, which means at least 0 bronze. And we want to choose 4 amber cells such that no two are in the same row or column. And even so, this problem is hard to approach because there are bronze cells that can be scattered around anywhere, obstructing what we're trying to do. So again, we can try another induction. And here the base case would be A equals 0 and B equals 0. And this is just the fact that we have a 1x1 grid, we're trying to choose 0 cells. We just choose 0 cells and we're done. So now we want to show the inductive step. And to do this, we can try to remove a cell. And when I say remove a cell, we choose a cell and we ignore its row and column for the rest of the process so that we do not have any two cells in the same row or column. And then we would effectively create an A minus 1 by A grid from our A plus 1 by A plus 1 grid. But for now, we have an A plus 1 by A plus 1 grid, and we have at least A squared amber cells and at least 0 bronze cells. And we want to show that we can reduce this to an A by A grid with at least A squared minus 2A plus 1 bronze cells and at least 0 bronze cells by removing an amber cell. And first, we can notice that if there are 0 bronze cells, we are basically done. We can just choose everything along this diagonal. And in fact, we can do this for a small amount of bronze cells. For b equals 1, even b is less than or equal to 1. So actually, I'm already using b for something. So let's say n is number of bronze cells. Then if n is less than 2, we can just ignore its row and column and choose a longer diagonal. So like if this is the only bronze cell, we ignore this column and this row and this column, and we choose these amber cells. So we only need to worry about n is greater than or equal to 2. But note that if we choose any amber cell, there are at most 2a plus 1 amber cells we remove when we remove that cell. And if there are 2 bronze cells, they must either be in the same column, the same row, or neither. And if they're neither, we can choose one of their rows and the other's column and consider this point. And this point isn't guaranteed to be amber, it could also be bronze. But if that ends up being true, we have 2 bronze cells on the same row, so we can just resort to our other case. And here we remove this amber cell and we remove up to 2a minus 1 amber cells. And since a squared minus 2a minus 1 equals a minus 1 squared, our inductive step is done. And if they're in the same row or same column, it doesn't really matter. There are 2 possibilities. If there is an amber cell in that same row, then we can just consider that amber cell and remove it. And we are again removing at most 2a minus 1 amber cells, so our inductive step works. The other possibility is if the row is entirely bronze. Then we can consider the A by A grid below this. There must be a bronze cell somewhere in here, or else we can just choose along the diagonal again. And if there is a bronze cell there, its entire column must also have bronze cells, or else we can, like if there is a bronze cell here, and this entire column is not all bronze, we can choose an amber cell here, and again, our inductive hypothesis would be done. So then we must have an entire row and column filled with bronze cells. And then there are 2a plus 1 bronze cells from that. But our minimum amount of amber cells is a squared, and our amount of total cells is a squared plus 2a plus 1, which means the maximum amount of bronze cells is 2a plus 1. Therefore, all of these cells must be amber, so we can, again, just choose along the diagonal. And although this row does not, this column does not have to be the leftmost, it's effectively the same, because if we have something like this, we can choose like this, and it still works. And therefore, by induction, we have proved the base case of b is equal to 0, and equivalently a is equal to 0. And now we can go back to our original induction, which was for all a and b. We have already proved the base case for that induction by now, so now we move on to the inductive hypothesis. And we can start off by defining x is equal to the amount of amber cells minus A squared plus AB minus B, which is the minimum we were given, and Y is the amount of B cells minus B squared plus AB minus A. And we know that X plus Y is equal to A plus B plus 1 squared, which is the total amount of cells, minus the sum of these two, which is A squared plus B squared plus 2AB minus A minus B. And this evaluates to 3A plus B plus 1. By the pigeonhole principle, we have that either X squared is greater than 3 halves A plus B, or Y is greater than 3 halves A plus B. And because these are symmetric, just
Can you
assume.
write the PGP there?
Okay. And these are symmetric, so without loss of generality, assume that X is the one greater than 3 halves A plus B. Now we can see which way to induct, to A minus 1B or to A B minus 1. Intuitively, it would seem that we should induct to A minus 1B, because if we have enough amber cells such that we can remove this much, because there's so much overflow from the minimum, then we should try to remove amber cells. But then we would only have room to remove B minus 1 cells in the case that Y is equal to 0. And that's bad because it would be harder to guarantee that. So instead, we can induct to A B minus 1. And this is not yet final. And we will see that in an edge case, it'll be easier to induct to A minus 1B. But this is the main inductive step. And if X is large enough, no matter how many amber cells we remove, the minimum will still be satisfied for A B minus 1. So in that case, we would only have to worry about the bronze cells. In fact, we can see that this minimum is 2A plus B, because then the amount of cells that we would be able to remove is A plus A minus 1 is the decrease in minimum when you go from B to B minus 1, plus, so the amount we can remove is greater than A minus 1 plus 2A plus B. And the maximum amount we could physically remove is 2A plus 2B plus 1, because that's the total amount of cells. And this is less than 2A in 3A plus 2B minus 1, because the amount removed is strictly greater than this, and it's an integer, so we can say greater than or equal to A plus that. And from this, we're only considering A and B greater than 0, because otherwise our base case would finish. So we have that 3A plus 2B is greater than or equal to, this doesn't need to be strictly greater than, because we can move up to that much. So then we have 3A plus 2B is greater than or equal to 2A plus 2B plus 1. And then we have shown that no matter how many cells we remove, the amber cells won't cause an issue. The only thing that could cause an issue is the bronze cells. And the decrease in minimum for our bronze cells is, it goes from B squared plus AB minus A to B minus 1 squared plus AB minus 1 minus A. So the decrease is 2B plus A minus 1. And we want to show that we can take enough amber cells such that this is not an issue. And first, we can notice that if we have X is greater than 2A plus B, the number of amber cells is greater than AB plus A squared plus 2A plus B. And now we can observe that this means that the amount of A cells is greater than or equal to AB plus A squared plus 2A plus B plus 1. We want to see what we can find about each individual row from this. And we can observe that this is equal to A plus B plus 1 times A plus 1. Which means that by pigeonhole principle, there exists a row with at least A plus 1 amber cells. And we want to remove a bronze cell, which means that the amount of bronze cells being removed in total would be, if there is a bronze cell in the row, it would be 2A plus 2B plus 1 minus A plus 1 as a minimum. And this is equal to A plus 2B. Okay, if this is, if y is equal to 0, then we have even more amber cells, and then we can find a row with at least A plus 2 by similar logic. And if y is greater than 0, then this amount of bronze cells removed is sufficient because there is a plus y here. And then we need to consider the case if there's no bronze cell in the row. And this is actually the case that I didn't solve when I did this in the contest. So we have an entire row of amber cells, and because this also works for column, we have entire row and column of amber cells. But then our decision to induct to A B minus 1 wasn't final. If we remove it was because if we remove the amber cell, our decrease in the amount of bronze cells might be too much. But here we're not removing any bronze cells if we just remove the amber cell at the intersection of the row and column. We're only removing amber cells. So then this just works. And then we have finished the case of x is greater than 2a plus 2b. Now we move on to the second case, which is where x is less than or equal to 2a plus b. Here, this also implies that y is strictly greater than a plus b. Then the amount of bronze cells being removed is, it can go up, the maximum for this, it can go up to, it's strictly greater than a plus b because y is strictly greater than a plus b. And you can add 2b plus a minus 1 because that's the decrease in the minimum. This becomes 3b plus 2a minus 1, which is enough. So therefore, we don't need to worry about this at all. For the amber cells, we can remove up to a minus 1 plus 3/2 a plus b because this is the minimum on x by assumption. It's actually greater than this. So that means that it is greater than 5/2 a plus 3/2 b minus 1. If a is greater than or equal to b, this is large enough, such that we also won't have to worry about a, because even if we remove up to 2a plus 2b plus 1 amber cells, this is more than that, or at least equal to that. So now we have to deal with the case where a is less than b. Then we have to consider the amount of bronze cells we can find. So there are at least, wait, actually, we want to, okay, so the difference from what we need here is B minus A over 2. So we want a row or column with this. And then we would be fine. And it suffices to, actually we need 1 plus this because of this minus 1 here. So we want a row with B minus A over 2 plus 1 bronze. And to find this, we can again use pigeonhole principle. We have that for the sake of contradiction, assume all rows have at most B minus A plus 1 over 2. And I move the plus 1 up because we want things to have strictly less than this for the sake of contradiction. Then we have the amount of bronze cells is at most B plus A plus 1, the amount of rows, times B plus 1 minus A over 2. And we want to show that B plus A plus 1 times B minus A plus 1 is greater than or equal to 2 times B squared plus AB minus A. And in fact, we have that B squared plus 2B plus 1 minus A squared is greater than or equal to 2B. This is less than because we want to show that there's not enough bronze cells, and this is the minimum. So we want to show this. And if we rearrange this, this simplifies to A squared plus B squared plus 2AB minus 2A minus 2B plus 2 is greater than or equal to 3. And this means A squared plus B squared plus 2A minus 1 B minus 1 is greater than or equal to 3. And the minimum for A and B are each 1. So the only case in which this inequality wouldn't hold, because this is non-negative, this would only not be true for A equals 1 and B equals 1, which either we could deal with that case especially, or we can use the fact that we can tighten this further. And actually now I'm realizing that this, we can even add to this, the minimum value from X and the minimum value for Y, because as X is less than or equal to 2A plus B, Y must be strictly greater than A plus B. So we can also add A plus B to this quantity, and then this becomes that we want to show A plus B squared is greater than or equal to 1, which is always true. And by this, we are able to induct down to a smaller case, and by induction, our proof is complete. So in summary, we turn to induction because this problem is complicated and induction is usually a helpful tool. And for the base case, which was when one of the values is 0, we again use induction to show that we can always remove a row or column. And
before you summarize, I have a question.
Yeah.
Can you explain why were you removing bronze cells and what does it mean to be enough? You did not explain that. So
when I say remove, I mean that I choose a cell here, and I can no longer choose a cell anywhere here, or else this condition will not be satisfied. So instead, I just fully remove these rows from the grid. And when I say enough, I mean that there should be at least the new value of A squared plus AB minus B amber cells, and at least the new value of b squared plus ab minus a epsilon cells. And after I proved the base case by the removal arguments, I show the inductive step by considering the overflow, which must exist because the minimum is significantly lower than the actual amount of cells. And this is enough such that in either case, we can fully ignore one of the colors. There is just enough cells such that no matter how many we remove, we can fully ignore it. And then we only have to consider one color. And by the pigeonhole principle, I was able to find a row which had enough of the other color such that we never remove too much of one color. And by removing that, I was able to reduce this to, I was able to prove the inductive step, which finishes the proof. And the reason this is one of my favorite problems was because this problem did not use any high-powered techniques. It was just like induction, and the motivation was never too obscure. And these are all reasonable to find. Like when you have enough of an overflow, it would be reasonable to consider how you can use that overflow to help your arguments. And are there any questions? Okay, moving on to the next problem. So this is asking for the amount of every function f, which does not need to be a polynomial, can be any function at all. And it should satisfy this condition for all real x and y. And again, this is a relatively simple problem statement compared to the previous two. And to start this, we should try one of the basic substitutions, which is just y equals 0 and x equals n for any n. This gives us f of n squared, no, f of n plus f of 0 squared is equal to f of n squared. We can call this value g of n. Then we can see that f of g of n equals f of n squared. And from here, it seems hard to draw any conclusions. So we can try substituting x equals g of n and see what we get. And also y equals n for all n. This gives that f of g of n plus f of m squared equals f of g of n plus m squared f of m cubed. But this is a bit complicated, so for simplicity, we can say m equals 0 for now. We then have that f of, this is just n, f of n squared plus f of 0 squared is equal to f of n squared plus n squared. No, it's just f of n squared. Okay, something seems wrong here, so I'm going to look at the previous step again. I'm going to rewrite it a bit larger. So we have that f of n squared plus f of n squared is equal to f of n to the 4 plus m cubed f of n, m squared f of n cubed. Yeah, this is still right so far. And then we can notice that this part is cyclic in n and m. So we can also say that this is equal to f of m to the 4 plus n squared f of m cubed. And for m equals 0, this gives that f of n to the 4 minus n squared f of, oops, this should be n, minus n squared f of n cubed is equal to f of 0 to the 4. But this isn't that helpful because we saw this n squared here, and we don't really have a relationship between n and f of n yet. So we want to eliminate the n squared, but we still want to know what f of n is. The only way we have figured out to do that so far is to say for all a substitute n equals f of a plus f of 0 squared. This gives that f of a to the 8 minus f of a plus f of 0 squared times f of 0 cubed is equal to f of 0 to the 4. No, this is f of a to the 6. And when we reduce this, we get f of a to the 7 times 2 times f of 0 squared plus f of a to the 6 times f of 0 to the 4 plus f of 0 to the 4 is equal to 0. This still doesn't seem too helpful, so we can just for now note the fact that this is a degree 7 polynomial, which means that there are at most 7 distinct values for f of a. And because of this, we can see what this amount of distinct values can do. 7 does not seem like a special number, so we just need to use the fact that there are finitely many values. And in fact, we developed this useful condition, which is that for all n, there exists z such that f of z equals f of n squared. So if the magnitude of f of n is not equal to 1, that n it's non-zero, there are infinitely many distinct values in range of f, because we can just infinitely continue squaring f of n. And this might be a bit hard to motivate so far, so instead we could have continued this further and gotten that if a equals 0, in order to make the terms more familiar, we got 2 f of 0 to the 9 plus f of 0 to the 10 plus f of 0 to the 4 is equal to 0. So f of 0 to the 5 plus to the 6 plus 2 f of 0 to the 5 plus 1 is equal to 0. And an obvious solution to this is -1. And also a solution to this is 0. If it's not 0, then we can reduce it to this. And 0 is special because if we look at the original equation, and I probably should have done this at the start, but trying around with some random functions for a while, like all linear functions or constant functions, the only one we can find that works is f of x equals 0 for all x. So we can just treat this as special and ignore it for now. Because usually in functional equation problems, you want to show that anything except the solution doesn't work, rather than showing the solution works for most of the part. And then this is the only value you can easily find, so we can consider what's special about it. And what's special about it is that it has magnitude 1. And that might motivate this a bit better. And then That means that the only solutions to this, like f of 0 can only be 0 or -1. Otherwise, it does not work. And from here, we can consider what happens if f of x is equal to 0 for some x. Then we can return to the problem statement. It says that f of x plus f of y squared is equal to f of x squared plus y squared f of y cubed. This seems to be the more annoying term, so we can substitute x into that. Then for all b, we have f of b squared, just f of b equals f of b squared. And by substituting the other way, we see f of b squared is equal to b squared f of b cubed. I think there's a better way for this. Yeah, this is not the right way. So from this, we can substitute x into that. For all b, we then have the f of b to the 4. Did I write? No, this is incorrectly, but we have a minus when we rearrange it. That gives that f of b to the 4 minus b squared f of b cubed is equal to f of x to the 4 minus x squared f of x cubed. And this is just 0, which means for all b, f of b is either 0 or b squared. And we want to show that f of b cannot be b squared. And to show that, we can now return to the problem statement. We can substitute x equals b, y equals b in the problem statement. And that tells us that f of b squared plus b to the 4 equals b to the 4 plus b to the 8. If b is not equal to 0, then this is non-zero, which means that it must be b squared plus b to the 4 squared. And this implies that b to the 6 equals 0, which implies that b is equal to 0. Therefore, the only case where f of b is equal to b squared is when b equals 0, and then that we also have that f of b is 0 because b squared is 0. And therefore, with f of x equals 0 for some x, it's also true for all x. Now we resolve the case where it's never 0. Then it must always be 1, nay, -1. But that clearly doesn't work because then we just have -1 equals 1 plus a minus y squared, which isn't always true. So that means that the only solution is f of x equals 0 for all x. And in summary, we use a substitution to find v for all n such that f of v is f of n squared. By manipulating that value, we found an expression with f of n and n, which is relatively simple. That is always constant. And by further manipulating that expression, we found that there is a closed set of the values of f of x for all x. And that tells us that no value of x can have a magnitude other than 0 or 1. And from there, we were able to solve the problem. One thing to note is that I never proved that f of 0 equals 1 isn't a solution to this, but if you substitute 1, you just get 4, which isn't 0. And the reason this is one of my favorite problems is because I feel like the steps were a bit hard to see, but they're connected in a way to the problem. This is not just like choose something random and hope that you get lucky and it leads to something, because it's fine. I think it's fine when problems are a bit unmotivated, but they still are implied from the results of the problem. I think the time is up, so should I do number 1 or just leave it?
So Rohan, what did you say?
Since it's past 4, should I do number 1 or not?
I think if you want, you can do. If somebody wants to drop off, they can drop off, but continue and do number 1.
First, are there any questions for number 5?
You have 2 problems left?
1 problem left.
Okay.
Okay, going to return to this problem now. So this is a diagram I had drawn before. I didn't want to draw it again because...
So Rohan, in this case, read the problem.
Yeah, I'm going to describe the problem through the diagram. The reason I didn't draw this diagram before is because in this problem, I think part of the motivation comes from having a good enough diagram, and I didn't want to have to redraw a good diagram in this time. And in this problem, we have a cyclic triangle A, B, and C. Its circumcenter. Then this point X is like B is the midpoint of AX. And then D is the intersection of CX and B. No, D is the intersection of CX and the circle. So then we have the ABCD as a cyclic quadrilateral, and we define E as the intersection of these sides, F as the intersection of these sides, and we already have that X is the intersection of these sides. The way I solved this problem in the contest was to observe that these definitions of F, X, and E were from the configuration of Brocard's theorem, and from there I was able to figure out P, but that's a bit high-powered, and it was one of the very few results that I knew at the time, so I don't present it here. I'll just write it in case anyone wants to know more about it. Where O is the circumcenter of ABCD. We have that this is true. Anyway, I'm going to try to avoid that here, and instead, what we want to see is whether this line EF can ever intersect the circumcircle of A and N, where M and N are the midpoints of AB and AC. And first of all, from our diagram, it appears like the answer is no, so let's work towards that. One other observation from the diagram we can make is that these lines seem perpendicular. And this is a benefit of having to scale diagrams. And I think it would be a bit hard to find without that. Anyway, another observation is that there is a circle here. It's a bit hard to deal with circles generally, and they're also an indicator of power of a point. And one thing that the question is if there's a correlation between this perpendicularity and power of a point. In fact, O is the circumcenter of triangle AMN, while B is not the circumcenter of anything. If B were the circumcenter of anything, then if we could show that EF were the radical axis of OB, in O prime B, this is O prime, not O. If EF were the radical axis of those two circles, then we would, the radical axis is the set of points which have equal power of a point with respect to both circles. From that, we would be able to determine the location of P. However, there is no circle centered around B. We can deal with this by considering the circle center of radius 0 centered at P. So basically just the point B. And in fact, results like power of a point and radical axis work perfectly fine with circles of radius 0. So we can continue like this. To show that it's the radical axis, we must show that both B and F have equal power of points. Oops. Okay, so first we can show this for E. So to show they have equal powerful points, we want to show that En times EA equals EB squared. And that's equivalent to showing that triangle EBN is similar to triangle EAB, or that angle EBN is equal to angle EAB. And then we would be done by angle similarity because angle E is shared between them. And now we can do a bit of angle chasing. We have angle EBN. One thing we haven't used that is that BN is parallel to CX. And this is because B is the midpoint of AX and N is the midpoint of AC, and BN is the midline of triangle ACX. Therefore, they're parallel. And because of that, angle EBN is also equal to angle EDC. And angle EDC is equal to 180 minus angle BDC. But BDCA is a cyclic quadrilateral. So this is also equal to angle EAB. Therefore, we have these two are equal, and we have the desired result that E is on the radical axis. Now we can do this for F. We do not yet know how to compute the partner points for F about the circle centered at O.
Can you write E is on the radical axis of which two circles?
And we can now try to see how to compute the powerful point of F. For that, the most logical way would be to use the line AF, because that's the only line with any points we know on the circle so far. But we only know one point on the line, so we want to find the other. In fact, the circumcircle of AMN is a homotopy of the circumcircle of ABC with respect to A and radius, no, factor half, which means that if we take the midpoint of AD, which is D prime, that is also on the circle. Therefore, we want to show that FD prime times FA is equal to FB squared. And it also suffices to show that triangle FBD prime is similar to triangle FAB. And again, it suffices to show that angle FBD prime is equal to angle FAB. And we can call this angle we can mark it like that. And because actually, I think it would be easier to work from this first. Because ABCD is cyclic, the other angle BAD and BCD are equal. Now, we can note that, again, B is the midpoint of AX, and D prime is the midpoint of AD. So BD prime is the midline of XD. So BD prime is parallel to XD, which means that this angle is equal to this angle. And therefore we have our desired result. So F is also on the radical axis. And the radical axis of two circles is always a line perpendicular to the line between their centers. So that means that first of all, line EF is perpendicular to line O prime B, and also the radical axis must be the line between E and F. And we can define P as the intersection of AB and EF. Then we have that PM times PA equals PB squared because it's on the radical axis. And by doing a bit of algebra, we can define S equals AB. Then we have, let's say, RS PB. Like RS is the distance of length of PB. Then this is 1/2 minus RS, and then half S. So we have half times half minus R equals R squared. 1/4 minus half R equals R squared. 4R squared plus 2R minus 1 equals 0. And this tells us that R should be equal to 1/3. And if you substitute 1/3, you get that. I must have got the algebra here somewhere. Okay, yeah. This is not half. You want PA, not MA. So this should be 1 minus R. And then 2R squared is equal to 1 minus 3R plus R squared. And plus 2R squared. And then we just have R is equal to 1/3. And now we know the location of P with respect to A and B. It just remains to show that the line EF can never intersect the circle. And that means that no point on the line can be a distance of R away from the circle, where R is the radius. And if any point is within R of the circle, then that will be false. And the closest point to the circle, when I say the circle, I mean its center, is just the foot of the altitude from O prime to EF, which we can call Q. And we can use power for points again, where we don't yet know if Q is on the circle or not. In fact, we're claiming that it isn't. All we know so far is that angle PQB is right. Therefore, PQ is less than PB, which is equal to 1/3 S. We can define omega as a circle centered at O prime and going through Q. Then power of a point on P with respect to that circle tells us that PQ squared is equal to PO prime squared minus the radius, which is O prime Q squared. Or this is just Pythagorean theorem, I guess. And this is less than 1/9 S squared, which means that O prime Q squared is greater than PO prime squared minus 1/9 S squared. And this time we use power of a point, not Pythagorean theorem, on the circumcircle of A and N about P. That tells us that PA times PM is equal to PO prime squared minus R squared, where this is the radius. And as we found earlier, this just turns out to be 1/9 S squared, which means that R squared is equal to PO prime squared minus 1/9 S squared. So the distance of O prime Q to Q is greater than R. And that's the smallest distance to any point on the line, which means that no point on the line can be inside the circle, and therefore we are done. In summary, by using powerful points with the respect to the circle of radius 0 about B, which is the point B. Through a bit of angle chasing, we found that the radical axis is EF. And through that, we were able to determine the location of P. And from there, we were able to finish by considering the closest point along the line to O prime. And one of the reasons this is one of my favorite problems was because of the idea of taking the circle of radius 0, which is something that is very interesting, as it seems like it would not work, but it does work. And also, the angle chasing wasn't too much, and I think the idea of choosing the foot of the altitude from O prime to EF was creative and interesting. Are there any questions?
Rohan, can you tell what is this contest USEMO?
Oh yeah, USEMO is, I don't remember if it's supposed to be like,
US ARSAD's Math
yeah,
Olympiad.
I remember its name, but I don't remember if it's supposed to be practice for USAMO or IMO. They're around the same difficulty but different styles. But it's a practice for one of them. It's run by Evan Chen around the end of October, and this is one of the few Olympiad contests that is open for everyone. Well, mostly everyone. You only have to be a US resident and not have won any prizes before. Are there any questions? Okay.